one interesting aspect of these Taylor expansions is that, well, we have the the value of the remainder, which is in a sense the value of the error of the approximation that we are making, right? So we can try to approximate values of known functions, and we will know what's the error that we are making, right? So we can make an upper bound of that error and say, well, the logarithm or whatever is equal to this, and the error that I'm making is smaller than this. Okay, so for instance, let's see. Let's start with the sign. Okay, we know, if you remember, the sign is x minus x cubed divided by 3 factorial plus the remainder of this is a polynomial of 4th degree, right? See, and then the remainder has this form. This is the 4th derivative of this is the 5th derivative, sorry, of the sine, which is going to be the cosine at some point c between 0 and x, but again we can write this as the cosine of theta x, where theta is between 0 and 1, divided by 5 factorial, which is 120, right? This is 5 factorial times x to the 5, okay, and then theta is between 0 and 1, right? Now yeah, is, because if we knew it, then we could compute the value of the sine wherever, okay? But we know that the cosine is, the absolute value of the cosine is going to be smaller than 1. So we know that the remainder is going to be smaller than x to the 5th divided 120. So this is the absolute value as well. So this gives you the absolute value of the remainder, sorry. This gives you an upper bound for your error, right? So suppose now we want to compute the sine of 0.1, right? So this is 0.1 minus 0.001 divided by 6, and then plus a remainder, right? And so what this we can compute, this is equal to 0.09983333, and so on, okay? But we know that this is 0.1, right? So this is x is equal to 10 to the minus 1. X to the 5 is equal to 10 to the minus 5 divided by 120. So we know that the remainder, if you compute this is going to be smaller than 8.3 periodic times 10 to the minus 8. Okay, so this is the approximation, sorry, this is the approximation of the sine. Let me rewrite this, okay, using the Taylor polynomial up to 4th degree. This is approximately equal to this. This is equal to this, and the sine, the absolute value, so the actual value of the sine, if you compute it, is 0.0998333, and then 41664, whatever, right? So then we have all of these decimals are correct, and then we have this small error here, right? So you see that the approximation is very good for a very simple approximation to the sine, actually, right? And in fact, when we you go into a calculator and you approximate, you type the sine of whatever number you want, what the calculator is doing is actually approximating the value of the sine using a Taylor polynomial. Or sometimes it uses better approximations that for some functions we know are better and have smaller errors for fewer terms, but the main idea is this one, right? So you can use these approximations to get as close to the actual value of the function as you want, right? Now we can think of this in another way. Instead of choosing the remainder in a sense and see what's the error, we can say, well, I want my remainder the error of my approximation to be smaller than 10 to the minus 5, for instance. Okay, that's the maximum value of the error that I will accept. So what's the maximum value of x that I can approximate with that error, right? So if we can substitute here, so this is x to the 5 has to be smaller than 120 times 10 to the minus 5. Okay, you can compute this. This is 120, this is equivalent to the absolute value of x being smaller than the fifth root of 120 times 0.1, which is approximately equal to 0.26. Okay, so values of x between minus 0.26 and 0.26 will be approximated with an error of smaller than 10 to the minus 5, which is, you know, nice enough. Okay, and now let's see. Let's see another example. Suppose now we want to compute the square root of 3.8. What's this? Okay, well, we can expand the function. The closest function that we can think of is 4 minus x, right? And we can expand it around 0, right? So let's have this function f, and let's compute its derivative, right? So we have the first derivative of x is minus 1 divided by 2 square root of 4 minus x. The second derivative is going to be minus 1 again divided by 4 times 4 minus x to the 3 halves. The third derivative is going to be minus 3 times 8 4 minus x to the 5 over 2, right? And then we can evaluate this. F at 0 is 2, f prime at 0 is going to be minus 1/4, f second at 0 is going to be minus 1 divided by 32. Okay, so then we have, using our polynomial up to second degree, right? So the square root of 4 minus x is going to be 2 minus x divided by 4 minus x squared divided by 32. But remember, we have to divide the second derivative by 2 in this term, and then we have the remainder of our second order polynomial x at 0. The remainder is our derivative minus 3 divided by 8, 4 minus at some point c, right? C to the 5 halves divided by 4 factorial, and then we have times x to the, sorry, x cubed. So this, yeah, this is not 4 factorial, it's 3 factorial, sorry. But then 3 and 3 go out, and then you have 2 multiplying 8 here, so you have minus 1 and then 16 here. Okay, this is our error that we're making. And okay, so now if x is greater than 0, and that's what we want here, right? We can say that our remainder, the absolute value of it, is going to be smaller than x cubed divided by 16 times x 4 minus x to the 5 over 2, right? Because from 0 to x, this function is increasing, right? So this is equal to x cubed times 16, sorry, divided 16 times the square root of 4 minus x, all of it to the 5, right? So now we can estimate the value of the square root of 3.8 as the polynomial here at when x is 0.2. So this is 2 minus 0.2 divided by 4 plus, and that's 0.04 divided by 64, so this is a minus, right? And this is so this is approximately equal to this again. approximately equal to this, and this is equal to 1.949375, and the error that we're making, this is going to be the remainder at 0.2, and we know this is going to be smaller than 0.2 cubed divided by 16, and then here you see that this is the same approximation here. So we have 1.949375 squared, sorry, to the 5. If you compute this, this is approximately equal to 1.78 to the 10, so times to the 10 to the minus 5. Okay. Now if you compute the actual value of 3.8, it's actually equal to 1.94935 and then 8, whatever, right? So then the first 4 decimals are the same, and then the error is in the 5th decimal as we expected. Okay. Now another use of this approximation is we can think of, instead of trying to bound up the errors, as we said, what's the maximum x that we can approximate with this polynomial. We can think of what is the highest or the degree of the polynomial that we need to, what degree do we need so that our approximation, the error, is below a threshold. And in this case, what we want is that the general formula for our remainder is going to be the n+1 derivative at c divided by n+1 and then x minus a to the n+1, right? We want that to be smaller than some, epsilon, which is the error that we want, right? And so that will depend on the derivatives of our function, and but we can make an upper bound of this. So depending on the example that we are working with, then we can solve this equation, this inequality for n, right? So if we keep increasing n, at some point we will reach our desired threshold. Okay.